In this video, we'll introduce complex power, or power as a complex number. We've introduced components of complex power already, all components except for one. So what we're going to find is that the magnitude of complex power is the apparent power. That's our S, or the magnitude of our phasor S. The real part of complex power is the average power. So we sometimes refer to average power as real power. The imaginary part of complex power we haven't looked at yet. That's reactive power. We use the symbol Q to represent reactive power. So that's a new term we'll introduce in this video. The angle of the complex power, that's the power factor angle. We've talked about the power factor angle. It's the same as the impedance angle, and it's the difference between the voltage and the current, the phase angles between the voltage and the current. So we can look at complex power on our imaginary versus real axis. And what we have is what we call the power triangle. The hypotenuse of the triangle is the magnitude of the complex power. That's our apparent power. On the real axis, what we have is the real power, or our average power, P. On the imaginary axis, we have the Q, the reactive power. And this angle here, that's our theta V minus Phi. That's our power factor angle, or it's our impedance angle, or theta V minus Phi. So we can represent our complex power in rectangular form or in polar form, as we can with any complex number. So if we imagine that we are driving a linear network that has a voltage across it defined as V effective, our RMS value. Our RMS voltage has an amplitude V effective and angle theta. It's driving a current into the linear network. It has a amplitude I effective, angle phi, and it satisfies our passive sign convention. Our average power then is, because we're using RMS values, we drop the 1/2 factor, so it's just the product of the voltage and current amplitudes, cosine of the difference between the angles, theta V minus Phi. If we make use of our Euler's identity, or Euler's formula, as we did with phasors, then we can take this product here, and we can get our V effective, I effective, the real part of our complex exponential J theta minus Phi. That gives us our cosine theta minus Phi. That's the real part of that. It's the real part, actually, of our voltage phasor, or voltage phasor represented in complex exponential, and not quite our current phasor, because we have negative J phi. So that's the complex conjugate of our current phasor. So we can say it's the real part of our voltage phasor times the complex conjugate of our current phasor. This is going to be an important formula for us to be able to recognize and use. So in summary, if we have a defined voltage phasor and current phasor driving a linear network, the real power, we can say then, is the real part of the voltage phasor times the complex conjugate of the current phasor. This is a new way for us to calculate our average power, or our real power. We started out with a general definition of average power in terms of the integral of the power over a time interval and dividing out the time interval. Then we said with a sinusoidal varying functions, that was just 1/2 of the voltage amplitude times the current amplitude of those sinusoids times the cosine of the phase difference of the two of the voltage signal minus the phase of the current signal. If we used RMS values, we could drop the 1/2 factor. And now again, we're saying if we're using RMS values, we can just say it's the real part of our voltage phasor times the complex conjugate of our current phasor. So in summary here, our complex power, that's our voltage phasor, complex conjugate of our current phasor. We can write that out in our complex exponential form, or we can write that in polar form, where the V effective, I effective, those two, the magnitudes of those phasors, that's our apparent power, when the magnitudes of these phasors is represented in RMS value. The angle, theta V minus Phi, that's our power factor angle, so we can represent that in polar form or complex exponential form. We could also represent it in rectangular form. So in rectangular form, when we expand our voltage phasor times the complex conjugate of our current phasor to one complex exponential, then the real part is the voltage times the current times the cosine of the difference of the angles, because that's because it's e to the j times the difference of the angles. So we're just using, again, our Euler's identity, and then our imaginary part with the sign. So that our average power, that's the real part, our reactive power, that's the imaginary part, and we give that a Q. So reactive power is what's new. Average power we defined earlier. So let's take a further look then at our reactive power. The physical interpretation of that is it's the time rate of energy flow back and forth between the source and the reactive components of the load. Remember, reactive components, the inductor and capacitor, they're going to absorb energy, but they can also supply energy. So they can push current back towards the source. So we can also interpret that as the charging and discharging of the reactive components. It's measured in VARs, VAR for volt amp reactive. We call those VARs. And by the unit, we'll be able to tell that that's the reactive power. Most industrial loads are inductive, so often these VARs are referred to as magnetizing power, the power to energize the magnetic fields in the inductors. So in summary, what we have for our units of power, we have our average or real power, we have our reactive power, we have our complex power, and we have our apparent power. So we can think of them all as components of this complex power. In rectangular form, as our P plus JQ, or our average power plus J times our reactive power. It's the V effective, I effective angle, theta V minus Phi, that's our apparent power angle, power factor angle. Or we can express that as our voltage phasor times the complex conjugate of our current phasor, making sure we see that all of these have the subscript EFF. That's equivalent to saying it's RMS. So these are our RMS values, so we don't have the 1/2 factor. And this is the basis of studying power. So this is a very fundamental basis of studying power. We can refer to our power triangle to help us work with complex power. We can get information at a glance from this power triangle. If we have two, we have, for example, the apparent power and the average power, then we can come up with our entire complex power. So we just need two. We can find all the others with our trig. Noting again that our power factor angle, that's the same as our net impedance angle from the perspective of the load, and it's the voltage phase angle minus the current angle of those phases. So if we do the tangent of theta z, this angle here being theta z, the tangent is Q over P. What we've looked at when we're looking at just impedances, the tangent of theta of z is our x, our reactance divided by our resistance. So we've already looked at this triangle in terms of an impedance triangle. So when we're working with power, we work with these power components as opposed to our impedance components. So again, our real power, that's our apparent power cosine of theta z, where theta z is the power factor angle, and our reactive power, that's our apparent power times the sine of theta z. Again, theta z is our power factor angle. However, we know that we can have a power factor that's leading or lagging. We know that that leading or lagging refers to the amount that the current is leading the voltage. So if our impedance angle is greater than 0, then our power factor is lagging, we have an inductive load, and our reactive power is going to be greater than 0. If our impedance angle is less than 0, our power factor is leading, we have a capacitive load, and our reactive power is less than 0. So that's when we have our triangle in the fourth quadrant as opposed to in the first quadrant of our imaginary real axis. So again, in review, for power measurement, we use a watt meter to measure real power that's drawn by the load, and it's measured in watts. Typically, it's measured in kilowatts. We have a VAR meter that reads the reactive power drawn by the load, and that measures the VARs. We have a watt-hour meter that records the real energy over time. and typically you're charged by the power company in kilowatt hours because you use that much. And a var hour meter, that's again reactive energy over a period of time. So distinguishing with these power measurements, what we're reading when we have a watt hour meter or a var hour meter, that's measuring energy. It's not measuring power. It's measuring the energy times the amount of time that you've used that energy. Let's look at one more thing here. What's important to understand is that our complex power is commutative. We can add up. We should have conservation of complex power. Our complex power, we said we can calculate that as our voltage phasor times our current phasor if we're using RMS values. But it's not the current phasor, it's the complex conjugate. The splat here means the complex conjugate of our current phasor. So we can also say that that's equal to our voltage phasor. If we have these two currents, I here is going to be equal to phasor I1 plus phasor I2. But we can say that that's equal, the complex conjugate of this phasor I, that's the complex conjugate of the sum of the currents, the complex conjugate of that. We can break that, which is obvious, but we can break that into these individual. This would be our S1 and our S2. There's our S1. And the reason we can do that, of course, is because, for example, if our I1 is going to be equal to I1 phasor, that's equal to our I1 cosine theta 1 plus J, we'll do that here, J sine theta 1. So when we do the conjugate of that, let's do the conjugate of the whole thing, that just becomes negative, right? So the conjugate of that makes that become negative, and it's just the imaginary part. So our addition is commutative, so we can do that with the conjugate. It looks a little bit confusing because if this was a square, we can't say that if this was a squaring function, but it's a conjugate function. So in fact, then we can say that our S is equal to S1 plus S2, and we have conservation of complex power. So again, conservation of complex power, conservation of average or real power, the real part of complex power. We have conservation of reactive or imaginary power. We don't have conservation of apparent power. That's the magnitude of our phasor. All right, we'll do some practice in the next video.